The natural exponential is a common base to write exponential functions. It's chosen primarily because it's very useful in calculus. Even for those who aren't using calculus, it still provides a uniform base to express every exponential function. Let's recall how we defined exponential functions before. An exponential function is one that can be written as c times a to the power x. C is the initial value, and a is the constant multiplier, which we've called the growth or decay factor. The natural exponential can be used to model the same things as the previous form, but every natural exponential has this base e, and for that reason it's more standardized. So the natural exponential form is written c times e to the kx. C is the same initial value as the previous model. K is called the instantaneous growth and decay rate. E is a magic number approximately equal to 2.71. E is actually a number kind of like pi that doesn't repeat and doesn't terminate. Typically we'll just use the E button on our calculator, which carries that out to several decimal places. Before we go on, it's important to note that the value k is not the growth and decay rate as we've used that word before, but is called the instantaneous growth and decay rate. When we say, for example, that a population has a growth rate of 70% per year, we mean that each year we expect a 70% growth rate in the size of the population. An instantaneous growth rate instead tells us at what rate is the population growing right this moment, not over the course of the entire year, but at this very instant. In general, the growth rate and the instantaneous growth rate are not the same. So how can we set up a model if we're given all this information? If we have a population of 100 bacteria with an instantaneous growth rate of 125% per hour, then we simply substitute in all the information. Our initial value is 100, our instantaneous growth rate is 1.25, and so I have a function 100 times e to the 1.25 t, which models the population after t hours. It's important to keep in mind that even though e is a letter, it just stands for a number that's approximately 2.71. The only variables here are the input t and the output f of t, which models the population. Since we were given an instantaneous growth rate, it was reasonable to use the natural exponential form, which has instantaneous growth rate as part of the definition. If we wanted to change this to our original exponential form, how would we do that? I can start with the function that I have. I'd like for this function to look like c times some number a to the power t. The initial value c is the same 100, and what will end up being my value for a is just the e to the 1.25 part. We have the numerical part set in parentheses, and the variable t is the exponent. Notice that e raised to the 1.25 power, and then raised again to the t power, is the same as e to the 1.25 times t power. When you raise something to an exponent, and then raise it again to another exponent, you multiply those two exponents together. So we've used that rule in reverse here to separate the two exponents. Now if I put e to the 1.25 in my calculator, it will say that it's approximately 3.49, and so the population can also be modeled by 100 times 3.49 to the power t. Writing a function in this way has the advantage that I have a better understanding of how the population is growing. An instantaneous growth rate of 125% per hour is useful for someone interested in calculus, but it doesn't give me much intuition about how the population is really growing. The form I have at the bottom has a growth factor of 3.5, and I can see that every hour I expect the population to multiply by about 3.5. This one's a very slight variation of the one we had before. I still have the population of 100 bacteria, but this time I have a growth rate of 125% per hour, not the instantaneous growth rate. Since I'm not given the instantaneous growth rate, I need to write in our original form. So my population can be modeled by the initial value 100 times 2.25 to the power t. This 2.25 growth factor comes from our formula that a growth factor is 1 plus the growth rate. So I used 1 plus 1.25 to obtain the growth factor of 2.25. How can I change this function to a natural exponential? I need to know the instantaneous growth rate k in order to do that. And the information I have is that e to the k should be the same as 2.25. Just like last time when we put e to the k in the parentheses and said that that was our value of a. This time I know the value of a, but I don't know what the value of k should be in the exponent. If we use a logarithm, we could get the value of k out of the exponent. And the log base e is a good choice for this, because it will cancel out exactly with e to the k. Just like log base 10 perfectly cancels 10 to the x, here I have log base e will cancel the e raised to a power. On your calculator, log base e is written as ln, which means natural logarithm. And typically in math text you'll see it written as ln. I just write log base e here to emphasize that ln is just another way of writing the log whose base is e. On the left-hand side, the log base e and the e cancel, and I'm left only with k. And on the right-hand side, I can evaluate this on a calculator, and it comes out to about 0.811. That means that a different population model, so the natural exponential model for this population is the initial population of 100 times e to the power of 0.811t. It's important to emphasize that the original model, 100 times 2.25 to the t, and the natural exponential model, 100 times e to the 0.811t, model the exact same situation. Their graphs would be identical, except that we've rounded slightly in computing the natural log of 2.25. Except for that small error, these two functions are exactly the same. They just represent two different ways to write the function now. So let me just repeat one of the laws we used here. We saw in earlier sections that log base a and a to the x are inverse operations. And that means that log base a of a to the x equals x, and it also means that a to the power log base a of x is equal to x. The fact that their bases match is what makes these operations cancel. This cancellation law is true for any value of a, and the particular one that we've used is the logarithm base e. So the natural log of e to the x is just x, and also e to the power natural log of x is equal to x. The bases here match, so they cancel out.